Okay, so in the last lecture, we talked about learning from simulation and how simulators can help us transfer knowledge and overcome some problems associated with reinforcement learning, for example, data efficiency, or how we can make use of privileged information to learn faster or learn better policies. So now what we are going to look at is how we can transfer knowledge, which is gained on some previous tasks that the agent has solved, and how it can, use that knowledge for new tasks, right? So in this lecture, that's going to be the topic of discussion. And I think the takeaway should be to understand what are different techniques which are there in context of transfer learning. And then we'll talk about what happens when tasks are presented in sequence, which constitutes continual learning and some catastrophic forgetting. So with that, let's jump into it. So the general problem is that if we have n tasks and then I'm provided with an n+1th task, then either I want to solve this task faster. When I say faster, I mean faster with respect to training from scratch on this task, right? Suppose if I had no experience of any other task, if I took, some amount of data to train, that amount of data should be, much larger than if I had some experience, right? And that is what we mean by faster. Or I should be able to solve a more complex task, right? That's the two scenarios or in which transfer is useful, or we would want transfer for those reasons. Now, as you all know, and we also look briefly, is that ImageNet, we got a lot of success in training these neural networks which take images and output image categories. But what about now we change the task, right? And the whole knowledge of classification is embedded in this neural network, right? Because this is what constitutes a model from image to the output. But now suppose we have a new task, and now I want to discriminate between apples and oranges, right? So what can we do now? Right? So essentially what we want is, we have these apples and oranges, and given one image of either an apple or an orange, I want to classify, is it an orange or is it an apple, right? That's the question that we're dealing with. But the problem is that apples and oranges are not in the training set. So what do we do in that case? So we can't just run an image of an apple and an orange through this network, because this network only knows about ImageNet categories. And maybe apples and oranges were not present in the ImageNet data set. So what we would want to do is we would want to say, well, the parameters of my network trained on ImageNet is say theta ImageNet. And I want to somehow change these parameters and make them the parameters appropriate for classifying apples from oranges. So this is one choice that, this is one way you can approach the problem. The other way, and if you're doing this, what we can do is we can take the ImageNet parameters, reinitialize the last layer, because the last layer might be specific to ImageNet categories, right? So maybe there are 1,000 ImageNet categories, but now I only need 2 categories, oranges and apples. So I can, randomly initialize just the last layer, keep the rest of the network to be the same. Why? To keep it the same, because we are hoping that the rest of the network has learned some useful image features which can be reused for solving the new task that we have at hand, right? And then we can train with SDD with say NFT examples, right? Where NFT are the number of examples from the apples, oranges data set. And this process is called as fine tuning. Now, what is fine tuning? I take some model which was trained on a previous data set. That process is called as pre-training. So I have a pre-trained model, which is theta ImageNet. I get NFT examples of a new data set, and I fine tune or I adapt the parameters with SGD, which is known as fine tuning. So this is one way we can approach the problem of classifying apples from oranges. The other way is that we can start with a random set of parameters, which is I initialize the network randomly, and then I do SGD with say n scratch examples. And this is what is called training from scratch. What the scratch means that I'm initializing the parameters without any prior knowledge. So they are initialized randomly. And our hope is that we will require much fewer examples if we are doing fine tuning as opposed to training from scratch. So what is this hope based on? This hope is based on the fact that this network trained on images has some knowledge about what are good image features, right? And that is why we should see this benefit. So practically, how do we do this? We have a network trained on ImageNet. Suppose we have a new task where I'm trying to predict the pose of a person, right? So over here, each line over there denotes the location of some key features of the human. So I take this network, and I replace the last layer to output, maybe some points, and I, adapt the parameters using SGD. Right? That's pretty much what we are doing. So, although our hope is that, NFT is less than n scratch, now this does holds in practice. For example, in ImageNet, each category has around 1,000 examples for each class. But typically, even if you have only 50 to 100 labeled examples for new classes, you can learn quite well with them. So these things, fine tuning works quite well if you have 50 to hundreds of labeled examples. But if you only have say 1 to 10 examples, it starts to get a bit more tricky. And the question which we are going to ask is, why does it get tricky? Now, before I go into this question, are there any questions that you may have? So I do see a question from Dhruv saying, is just changing the last layer enough? Would there be cases where it needs more than this? So I think just to be clear, what I meant is we reinitialize the last layer, but we can train all the layers, right? We are not constraining ourselves to training just the last layer. Any other questions? No? If not, then, I do have a poll for all of you. And, this poll is about, fine tuning with very few data points, right? So hopefully now you should see the poll, right? And the poll is, fine tuning with very few data points is not effective because, and there are a couple of options. So I, encourage everyone to, go through the question and, vote on what you think is the most relevant answer. So, let's take, 30 seconds. So when the timer becomes 1, I'm going to stop it. So it seems like, we have 10 seconds to go for the poll. So now, if you're on the edge, now is the time to, make your choice. Okay, last 5 seconds for people still on the fence. Okay, now I'm going to end the poll. And, let's see what the results are. So, okay, so it seems like there's a tie between the first two things. So the first answer was the model parameters theta will not change much, and thus the performance on the new task will be poor. And the second is the model will overfit on the new task, but not transfer. So, so does anyone, or maybe, who answered the first one, the first choice, want to, comment or, say why do they think that is going to happen? Or maybe anyone who went to the second answer, right? Model will overfit on the new task, but not transfer. Why do you think the first may not happen? No responses, huh? Seems like everyone wants a cup of coffee. It's Tuesday morning. Still nothing. Okay. So one comment which came along was, if we do not have enough data points on the second task, we may not understand the relevant features of the second task. So that point is very well taken. But there are, two things happening over there. Right. So one is about overfitting on a task, and the second is will we transfer or not, right? So those two things are two separate things. For example, my training loss can become really small, but I may not end up transferring, right? So consider an extreme situation where I only have one example per class and I'm training a giant neural network on that data, right? It's very likely that I am going to overfit, or I am going to memorize that data set, right? But because I do not understand the features which are relevant, I may not be able to transfer. So even if I have few data points, if I do a lot of SDD updates, we can obviously, or we can many times or almost always overfit, or we can, again, let me rephrase that, right? If we have a few data points and if we do SDD for enough iterations, we can almost always minimize the training loss and make it zero. So most likely what is going to happen is that the model is going to overfit on this new data set, but it may not end up transferring to new examples of the same data set. So does this make sense? Any questions on this part? So I realize there might have been an ambiguity in the first part because it says the performance on the new task will be poor. I think they should have mean the training performance on the new task will be poor. So, so how do we end up resolving this problem that I might end up overfitting to these very few data points, right? So there are a couple of well-known tricks. So one is when we are doing fine-tuning, we typically use a smaller learning rate than what we would use when we are training from scratch. Many times people would use 1/10 the learning rate that they would typically use if they're learning from scratch. Right? Then the other possibility is to only train the last layer or a subset of the last few layers. And as was pointed out earlier, are there, when should we train just the last layer or when should we train just the last few layers? I think that really depends on how much data is there on the new task that you're fine-tuning on. So for example, this is from a paper a while back. There is a task of doing object detection on the Pascal dataset. And what you're seeing is the comparison between fine tuning all the layers, which is FT, and fine tuning just the last two layers, which is FCFT. And these are accuracy numbers, right? So 54.1 and 53.3. So these numbers are quite close to each other. But if there is more data available on the new task, then of course you should tune all the layers, right? So I think this how many layers to tune ends up being a function of how much new data is available. Any questions on fine tuning before we move ahead? No? Okay. Does someone want to say something? I guess not. Okay. So the issue that we are left with is that fine tuning, despite the tricks that we discussed, might still overfit to these few data points. So what are some alternative methods in that scenario? Right. So again, re-emphasizing the problem setup. So we have one or a couple of images of apples and oranges, where X denotes the image and Y denotes the label. And at test time, I get a new image, and the question is apple or orange. So instead of trying to fine tune the features of this network, right, what if I just match or compare the representation of this new image with representation of images in my data set and find which one of them is the closest. So more concrete, or more mathematically, to be more precise, I can say, well, if I have my data set of n training data points, then I can compute the features of each of those examples, and then I can find this new image is close to which one of them, right? And then if I find that image, I can look at the label of that image and output that. So in this case, I am not really fine tuning the network, but I can, for example, take the pre-trained ImageNet network, or some mechanism by which I have learned features, and use that representation to predict the category of the image or the observation that I have. So this is classification based on nearest neighbors, right? A very powerful technique again to do predictions when we only have a few examples at our disposal. And this is much less likely to overfit, because we are not really tuning any parameters over here, right? All we are doing is we're doing an argument in the feature space. But whether this approach works or not, right? What does it depend on? Right? Whether nearest neighbors are going to give me accurate classification or not give me accurate classification. What is the fundamental thing that it depends on? Does anyone wants to take a guess, or comment on what that thing might be? So as was pointed out, the features that we are using, right? So whether nearest neighbors works or not really depends on the features, right? So for example, if I'm doing image classification, we do not really care about the location of the object in the image, right? Where the dog is, or where the cat is, or where the orange is. But for example, now if I was trying to predict the location of, say, where a particular star is in the sky, right, or where the river is, if I have imagery of some satellite imagery, then I need to be specific about the locations, right? So in that case, features for classification may not be so good, So what do we do in this case? So one thing we can do is we can learn to match features, right? So what do I mean by this? So the typical way we think about classification is to take a collection of images and predict the classes. But what about we flip the problem slightly and say, or we modify the problem and say, well, if I have two images which belong to the same class, then I'm going to predict an output as one, and where the images are processed through some featureization, let's say some function phi with parameters theta z, and then I compare the features of two images with some comparator, which is function f with parameters theta f, and I output one if they belong to the same class. And if they belong to different classes, we are going to output 0. And we're going to find parameters theta z and theta f so that this loss is minimized. So now what we're doing is we are explicitly learning how to match things instead of just learning to classify a given image. For this network architecture, where the features of both the images are processed to the same parameters and then compared, is what is called as Siamese networks. And this was proposed in work by Raya Hatzel in 2006. So this is also called metric learning. Why is it called metric learning? Because essentially this is giving you a distance function between these two images, right? Typically the output of the network is going to be a continuous value from 0 to 1, which gives you some notion of distance. So we're trying to understand, what images are close to each other, what are far away from each other. So one question which came up in the chat is, why do we need to optimize theta f? Can't we use our own functions to define distance between z1 and z2? Yes, you could, for example, define an L2 distance, or you could any distance of your choice. That also works. Typically, sometimes the distances may not be linear, right? So you might have to do some work, and therefore you put some non-linearity even in the distance calculation. But there are some occasions where you can just make it linear. That's fine too, or define your own distance metric. Any more questions over here? Nope. Okay. So how do we deploy this system? Now I have this new image. Now I have my original data set, right? So I compare first with the first image, I get this output. Then I compare this with the other image in my data set, I get this output, right? So now what is the con? The con is that I need to iterate through all images in my data set and then find this value for each of those images and then choose the maximum, right? Choose the image which was the most similar and then output its label. So, this approach of, learning how to match has been quite popular. So there are, two particular works. Both of these works have more than 1,000 citations at this point. One of them is matching networks, and second is prototypical network for few shot learning. These are based, on the idea that we just discussed. They are slightly more nuanced versions of what we talked about. For example, matching networks constructs a Siamese networks, but uses some form of self-attention. And prototypical network has, a slightly different objective function. So if you are more interested, I would encourage you to look at these works. Now, before we go ahead, I'll again take a pause and see if there are any questions. Okay, so let's move on and consider another perspective. So I mean, essentially, in the fine-tuning world, what we were trying to do was to change the parameters theta of some pre-training task to go towards a target task, right? So if I have my parameters theta, I get the first task apples versus oranges, I do fine-tuning, I try to go to theta 1, right? Then suppose I get a second task, dog versus cat, then we end up getting these parameters theta 2, right? So as I'm getting more tasks, I might end up fine-tuning to those tasks, one by one. Now let's assume that the amount of change of parameters that I need to make for the first task is delta theta 1. Similarly, for the second task is delta theta 2. So the amount of fine tuning, which I, have to do to maybe solve task 1 and task 2 is the sum of, you know, delta theta 1 plus delta theta 2. Right? Intuitively, the larger the delta theta is going to be, more data we will need, right? Because if I want to make big changes in my parameter space, I better be sure that those changes are good, right? And how do I become sure about that? If I have larger amounts of data on which my loss goes down. So if somehow we could choose the theta so that delta theta 1 and delta theta 2 are small, then we may require much fewer training examples or a much fewer fine-tuning examples. For example, in this scenario, now the theta was over here, then delta theta 1 and delta theta 2 are smaller. So in this situation, fine-tuning would be faster. Now, what do I mean by faster is it would require fewer data points. So the question we can ask is, can we optimize theta to make fine-tuning easier? Does the problem setup make sense? Or any questions on the problem setup? No? Okay, so how do we go about doing it, right? So suppose I have this, first task, which is apples versus oranges. Now I have my loss function of this task. And suppose I already have, this pre-trained network f of theta. Then what we do is we adapt the parameters theta using SDD, and we get to theta 1 prime, right? How do we get to theta 1 prime? Is by taking the gradient with respect to my loss function and doing the gradient update rule. Right? But now what I can also do is I can say, well, I want to change my thetas so that it is easier, or so that it is easy, so that my loss function at theta 1 prime is also low, right? So now I'm trying to change the theta to move it closer towards theta 1 prime. Right? That is what I am doing is, I'm training for faster fine tuning. Now, maybe it is not so apparent once I only have one task, but consider that I have now a collection of n tasks. Right? And what we want to do is to, at test time, I'm going to have some new tasks that I don't know about, right? And I want to do well on that task. So now what I'm doing is I'm trying to find, the parameter set of theta so that it is easy to fine tune to any of the tasks in my training data set. And that is what this objective function is, doing. So there are two steps, right? I am, always trying to find the theta from which fine tuning is easy. And then, I go and I fine tune. So this is, idea behind a bunch of, meta learning work which came along. So there is, low shot vision recognition, there is optimization as a model for few shot learning, and also model agnostic meta learning. So all these techniques, at some level are based on this, fundamental idea that we can choose a good initialization of my pre-trained of my pre-training so that fine-tuning becomes much easier. So yes, so I guess until now, what we have seen are some methods of transferring knowledge. We started with fine-tuning. Then the issue that we ran into fine-tuning was that if you have only a few data points, then I might overfit. We looked at one way of solving it, which was nearest neighbor matching. But nearest neighbor matching really depends on the feature space. So to learn the feature space, we can use Siamese networks. The other way to resolve the issue of fine-tuning is to say, well, how about I choose the parameters theta, so fine-tuning by itself becomes easier. And that is what is in scope of some of the more recent meta learning works which have come out. So any questions on any of these four methods that we went over? No. Okay, so let's see what are some issues which also happen when we apply any of these methods, right? So for example, suppose, so I mean, in some ways all of these methods essentially depend on how good my pre-trained features are, right? For example, if I'm doing fine-tuning, if my features are good, I may not require too much fine-tuning, right? My nearest neighbor matching is going to work well. Siamese network is trying to learn a good feature space, where metric learning is easy, or sorry, where making comparisons is easy. And meta learning, you can also think of it as trying to learn a feature space which has been optimized for transfer. So now, suppose I take, a dog image from, so from the internet, say from ImageNet, my accuracy could be 80%. But, if I take, dog image from the wild, my accuracy ends up being, say, around 20%. So it turns out that, one problem which still remains hard is how to get this initial good feature representation from which we can transfer. And so if we are in the domain of just internet images and we test on internet images, things work fine, right? I'm getting high accuracy. But the moment, I come to more real world data, which is this image of a dog from a very different viewpoint that you typically would not find on the internet, right? The accuracy drops significantly. So one question, we may ask is, why is this happening? So, consider, the following task. So I want to classify what a car is. So I say, car images, I end up getting these images, and I say non-car images. And suppose I end up getting, these images as non-cars one. And then we train a neural network to learn how to distinguish car from non-cars. And now suppose I have this new image and I'm trying to classify if it is a car or not a car. So now one question, which I want you to ponder about is, what do you think? What will the network predict? Will the network predict that this is a car, or will the network predict that this is not a car? Right. So I have just launched a poll for that. Right. So I encourage you to, think about this. And so again, I can show the training data set. How do I show? Yes, I can't go back without revealing the answer. So I'm going to, I hope you remember the training data set that was there. Yeah, so this was the training data set. Right, so we had a positives and a negatives. So we'll hold for 15 more seconds, and then we're going to close the poll. So it seems like we have got 17 responses, waiting for a few more. So if you're on the fence, now is the time. Okay, so now I'm going to close the poll, and let's see what we got. So 7 of you believe this image contains a car, and 12 of you believe that the image does not contain a car. So anyone who says the image does not contain a car, why is that? Okay, so one response is that there is no road in the test set. The other response is the train model may include many features from background, city, buildings, and so on. And other comment is the non-car images contained trees or grass over there, right? So let me stop the sharing. So if you look at all the negative images, they had some natural background, whereas all the positive images had just images of a car, right? So now over here, the network could pick up on any feature to say what a car is. We expect it is going to pick up on the car, but maybe just learn to discriminate road from something which is green, right? So this is a problem, what is known as learning spurious features, right? So why is it spurious? Because it minimizes the training loss as if it was the correct feature, but it is not the feature that we desired my architecture is going to learn, right? So this is a big problem in feature learning, right? So suppose if you have a pre-training task, but if you picked up on spurious features, then we may not be able to transfer to new tasks, right? So think of transfer learning. There are kind of two problems in transfer learning. One is given we have learned some features, if I get new data sets, how do I adapt these features, right? Which is fine tuning, Siamese networks, meta learning, right? Other is how do I learn good features in the first place, right? And a big problem in that is these spurious correlations, which cause an issue. Now, if you want to look at a paper, you should look at Antonio's paper from 2011. So they point out that there are data sets biases. For example, all non-car images look like trees, and all car images are on the road, is a bias in the data set, and that these biases are many times, are responsible for learning, spurious features. But there's also a very famous example, where DARPA, which is the Defense Advanced Research Projects Agency. So, you probably heard about it. So, sometime back, not by sometime, I mean a couple of decades back. So they wanted to researchers to build classifiers to detect tanks. Turned out that all the tank images they had were, from day, and all the non-tank images they had was from night, right? And then you probably know what happened once they tried deploying that model. When the US military tried deploying that model, it completely failed, right? So this is, a real problem. So just, to say it again, suppose I want to classify, this image as a dog. My desired hypothesis is to pick up on tails and eyes. But I could, learn something completely different, like to focus on a tennis ball and grass. And now if I have a distribution shift, which is now a dog is no longer on the grass, but in the water, I might think it is dolphin because there are many images of dolphins in the water. So, these, again, just to reiterate, deep networks like to cheat or learn unwanted solutions. So we will look at a bit of it in future lectures, which is the task specification problem of, what are some methods to overcome these unwanted solutions. Right? So one cause that we discussed was a dataset bias, but it turns out that even though you can create balanced data sets, there are still biases which creep in. Right? For example, if you're interested, you can look at the paper on the slides. Balanced data sets are not enough. Right? We'll talk more about this in a future lecture. For now, what I want to focus is, on one hypothesis, one very particular way of how we can overcome this problem. Right? So one intuition you could have is that if I have more parameters in the network, maybe there are more chances of learning, spurious correlations. Or maybe if I'm trying to learn a very hard task directly from scratch, I am more likely to find a spurious correlation. Right? But maybe what about if we first learn simple tasks and then we use these simple tasks to learn more complex ones? Maybe in that setup, I will not learn, as spurious features as I would learn if I'm trying to solve something very complex in the beginning. Right? So, so let's, build upon this intuition. Now, what this is saying is, maybe I have, task one, which I'm training on. Then I get to train on tasks two. Right? And maybe this way we can overcome some problems associated with learning spurious features. But once we start doing this sequential training, there comes about one more problem. Right? What is this problem? But now suppose I have these parameters theta2 which were tuned for the second task. If I go on the first task and compare performance and compute performance, turns out my performance ends up being quite bad. Right? The performance on task one is very poor. And this problem is known as catastrophic forgetting. So, to illustrate it, maybe more mathematically, I suppose I have my data set X and I'm trying to map it to the label space Y, and suppose the label space Y is given by this circle. So I've trained my parameters W1 for task one. Now suppose I have a second task, and what we do is the second task needs to be mapped to some other point in the label space, and we take W1 and we fine tune them to get to W2. Now what I do is I evaluate this new weights on the first task to get my predictions Y hat. Turns out now Y hat doesn't end up matching the ground truth. And this is, what is referred as catastrophic forgetting. Now, one thing you may say is, well, this problem is only going to happen if maybe these tasks are very different from each other. But turns out that's not really the case. I mean, the tasks don't have to be very different. For example, if I have this, training of trying to classify what class of digit this is. I want to say it's a 2, it's a 3, it's a 6, it's a 8. So this is suppose my first task, and I'm going to test on the same task, I get high accuracy. But suppose now I rotate all the digits by 90 degrees. Now if I train on this task now and I test on this one, the performance ends up being very poor. Right? So what I'm doing is I train first on this, I fine-tuned on this, I'm evaluating performance on same 0 degrees, right? So similarly, I can rotate it, by 90 degrees more, 90 degrees more, and so on. So if my data is coming in this particular way, right, where I first get, all digits at some particular rotation, then the rotations of these digits are changing by, 90 degrees and so on, then learning becomes quite hard, right? So think about, more practically, in the morning when the sun comes out, things look of a different color. As the sun goes down, the lighting changes and things, their colors change, right? Because sunlight disappears. So now suppose I trained my models, of images collected there was sun, when there was sunlight, right? And, then we, tested it on, and then, as the day progressed, we got more training data when the sunlight was lower and lower. But we were testing it when the sunlight was on, data from earlier in the morning, my performance could be pretty bad, right? Now, why does this typically, not show up in machine learning is because we never work with this kind of real data. What we assume is that once I get all of my data, I'm going to put them into some memory and just sample batches of data, and these batches are randomly sampled, right? So for example, over here, I will get batches where I have digits of all rotations, right? So that is what we mean by identically and independently and identically distributed data, right? That each batch has a similar statistic. Versus if the data was coming in, this way, suppose this was batch one, the second column was batch two, the third column was batch three, then the statistics of each batch is going to be different. So whenever we have such a problem where data is coming in sequentially and the statistics are changing, turns out that's a big problem in machine learning. Now in the real world, the data is often not batched, but in many scenarios we do assume that we have access to all of the data at once, right? So in some scenarios, this is practical or feasible. For example, if you want to just do image classification of, couches and cats and dogs, we can just collect the data by having a lot of photographs, right? But, for example, you want to put a robot in your house. Now this robot needs to keep on learning new things, right? Maybe you want the robot to cook something now, you want it to do your laundry and then it cook something else. So, it needs to learn new tasks, and these tasks are coming one by one, right? They're not all presented together. So, how do we learn in that setup? So to again, illustrate the problem, right? Suppose I trained on, say images of, 10 object classes. And then, I go to some other 10 classes, right? And then what we can do is, we can measure performance. And we're only going to measure performance on the first task, right? So what you see is after every 20,000 steps over here, we are going to add a new task, right? And as we are adding new tasks, when we're evaluating performance on the first task, the performance is going down, right? So which is again, showing the same problem of catastrophic forgetting. So now let's also see this in, case of, applying reinforcement learning. So what I'm showing you is this benchmark called ProgGen, where there are games and there are many, many levels of the same game. And the idea is to train RL agents which can generalize to new levels of the same game, right? So now what you can do is you can train RL agents with varying number of levels. And as you would see, if you are willing to train for around 100,000 levels of the same game, then the training performance and the testing performance, so training is shown as blue and testing is shown in orange, right? The training performance and testing performance end up matching. But when we are training over here, we are assuming that we can randomly sample all levels, right? So if I have 100,000 levels, I can uniformly and randomly sample every level, right? So this is IID training, in which case we can get transferred to work, right? I mean, it's a separate issue. You might say, well, it still requires 100,000 levels. We'll come to that in later part of the course. But I think the thing which I want you to focus on is, so instead of presenting all these levels in parallel, if you present these levels in sequence, there is no transfer. What you see is the training curves are increasing, but test curves do not, the performance is zero. So the sequential / continual learning, things completely fail in, this domain. If you just do some simple fine tuning or pre-training and so on and so forth, right? So these terms, sequential and continual learning, both are referring to the fact that I don't have access to all the tasks at once, but they come one by one, right? So, just to give one more example on ImageNet, instead of assuming that I have access to all 1,000 object classes at once, maybe first I train on cats, then I know what dogs are, then I know what bananas are, and then I know what tables are, then I know what chairs are, right? So if you give data in that form, learning is going to be hard. If you give all the data together, we can learn. But that may not be realistic in many scenarios. So, before we look into how to deal with catastrophic forgetting, any questions on what catastrophic forgetting is? Or what continual learning / sequential learning is? Any questions, comments? No, makes sense. Okay. So any ideas on how do we deal with this problem? How do we not forget tasks that we have solved in the past as we are going and solving new tasks? So what is the simplest thing one could do? Have something like a replay buffer, right? So one thing we could do is just store all the data that we have until now, and then we can keep on uniformly sampling from that replay buffer, right? So if I am willing to have a large memory, that solution is feasible, right? I could have, but then as the data set size increases, that solution may become harder and harder to practically implement, right? So but this also brings up a very good point, is like, so when is catastrophic forgetting really a problem, right? So I think if we have enough memory, then we can easily overcome it, because we can store everything and just uniformly sample, right? Then catastrophic forgetting is not really a problem. It is a problem when we just cannot fit data over a lifetime of an agent into the memory. So an alternative one could also do is to just remember weights for each task. Now this seems simple, and it kind of works, I guess it works by design, because if you remember weight for each task, you can always go back to those weights. But again, the problem is, you need to store all the models. The memory is going to be much lesser than amount of data, but still I need to store all the models. But suppose if I have enough memory to remember all the weights, is there any other issue with just storing the weight for each task? Or do we think that this will pretty much solve the problem? So suppose we say one task per model, right? So one comment which is coming up is we need to distinguish between the tasks a priori. So in the real world, if the data is coming in, you may not know when the task changes from one task to the other, right? But for the moment, let's assume that we know when the task is changing. So we could store models for each task, but the problem is going to be that there is going to be no transfer between tasks, because now I'm storing each model for a separate task and there's no crosstalk between models. So I cannot share information between tasks, right? So that becomes a problem in the naive approach of just remembering the weights. So, what kind of things have people looked at to overcome this problem, right? So one, set of ideas is progressive networks, which came along around 5 years back. So over there is some color coding. So red is the source task, and the blue, the red, if a layer, so this is a 3-layer network. If a layer is shown in blue, it means that that layer was trained or was optimized for the target task, right? So the simplest baseline that we can construct is to get a network from scratch and train all the layers for the target task, right? A second baseline, as we discussed before, was where we have a source network, but we freeze the layers. So all the dashed layers are frozen, right? We freeze the layers and we tune only the last layer, right? Or we could be tuning all the layers, right? All the source layers and the target layer. Now you could do some more things. You could say, well, I am I'm going to skip this baseline because this baseline is not as significant. But one other thing you can do is you can say, well, I'm going to keep my source layers fixed, but I'm going to create one more column in which I'm going to learn things which are relevant for the new task but were not represented in my first task, right? So I have the input, I pass my input to both the networks. The first network is the network on the original task and it remains fixed, but I compute features and these features go as input to the new network that I am training. And then if I get a third task, I will create one more column and then fix the previous two columns. So why is it called progressive nets? Because I'm progressively adding, one column by one column or one subnetwork by one subnetwork. So what has progressive nets achieved? What it achieves is that it is overcoming catastrophic forgetting by storing model weights for each task, but it is also able to share some information between tasks. So there are notions of two kinds of information sharing. So one is forward transfer, one is backward transfer. So what is forward transfer? Forward transfer is what you are seeing over here, where previous tasks information is helping future tasks, right? But the information from new tasks is unable to change how we solve previous tasks, right? To give you an example, right? I mean, suppose if I ask you, to come up with, uh, let's say, stack the towers of Hanoi, right? Or, let us say, I ask you to add a sequence of numbers, right? You can keep on writing a program which is a plus b plus c plus d and so on, right? But in the future, if you learn about recursion, then you can go back and change your code and redo how you did things if you never knew about recursion, right? So sometimes new knowledge can really help you perform your old tasks better, right? So that is what is called as backward transfer, right? And what is forward transfer? Forward transfer is when my current tasks are helpful in future tasks, right? So progressive networks is able to achieve forward transfer and overcome catastrophic forgetting. What it is not able to do is no backward transfer, and we do need to store weights for each task, which could be challenging in some scenarios. And what we're going to look in the next small section is, can we do something smarter than storing all the weights? And maybe just to give some context of why we are going through this transfer learning, catastrophic forgetting, continual learning. I think, I guess the course is about sensory motor learning, but as you will see, a large aspect of sensory motor learning will be to transfer knowledge from previous tasks, right? And these are some of just some fundamental issues which come up. So it's important to understand these problems, because these problems are going to become just tougher in context of reinforcement learning, uh, much more tougher than what they are in supervised learning, right? I mean, they're tough in supervised learning, but even tougher in reinforcement learning. So let's see if there are any questions on progressive networks. So I see one question, which is, what are the features being passed forward? Are they weights from the old task themselves? So they are features computed from the weights of the old task. Okay, so can we do something smarter than storing all the weights? So this has inspired a bunch of work. This question of, can we be smarter than storing all the weights? So one popular method which came out was this EWC. Now let me explain what this is doing. So suppose there are two tasks, A and B, and task A, suppose there are choices of parameters theta A. If they lie in this gray oval, then the error for task A is low. So suppose I learned some parameters theta A star for task A. Now suppose the range of parameters for which the error is low of task B is given by light yellow. So if I do naive fine tuning, what is going to happen is that this theta A star is going to move, and we're going to get to some theta B star. But now the error for task A is going to become very high, right? So somehow what we would want is to, instead of moving along the blue line, we would want to move along the red line, where we can find the set of parameters which work both for task A and task B, right? Without needing to store each model individually. So what does this work propose? This work proposes that as I'm optimizing for task B, I put some constraint on how the parameters theta should change. In particular, I constrain my parameters theta to be close to theta A star. But instead of just imposing the L2 distance between the parameters, what we impose is this Fisher information matrix, right? So, fisher information is again like is a way to calculate distance, which is more. It's a better measure than Euclidean distance. Now, if you're more interested, you can read more about Fisher information. I'm not going to get into it. I think that the takeaway that you can have is that I am trying to somehow constrain my updates to be close to my original task parameters in a way that I don't lose any information about my first task. And that is what Fisher information essentially calculates. And this method was known as elastic weight consolidation. And we can go and look at the performance. So if you look at the performance on the y-axis, and I'm seeing the number of tasks, if you just do SGD plus some kind of regularization, the performance really drops down. Versus for EWC, the performance is quite good. It's very similar to single task performance. The single task performance if I train for each task from scratch. So what we're able to do is that we are able to find, a way of fine tuning which does not lose information about previous tasks. Any questions on this part? Is this making sense? I mean, have I lost you? Are you with me? Any questions on this? I'm happy to explain again, if things were unclear or if, we went over it too fast.
Can you explain again what the Fisher information function actually does?
So, I mean, Fisher information, I mean, it's so, okay, let's assume that if I replace Fisher information by just the Euclidean distance, right, for just, for some time, assume that. What that would do is that would say, well, I want to be close to theta A star as I'm fine tuning, right? That is what L2 distance would do. But then measuring L2 distance in the parameter space is not very useful, right? So instead, we want to measure some notion of mutual information between parameters of task A and task B. So Fisher information is helping us measure that.
Okay, all right, thanks.
Okay, so now, but just imagine if I'm putting more and more tasks, right? I mean, then this space, suppose if I have task C, right? I mean, there's one more oval like this, right? So if I put more and more tasks, the shared space of parameters is going to shrink. So at some point, we will eventually run out of capacity to store information about all the tasks. Right? So one line of work, has looked at, is there a better way to make use of neural network capacity? So they have relied on this finding, that people have found. But suppose if I train a neural network, and if I get, say X% performance, then I can reduce a lot of the connections, and I can also delete many of the neurons, and we only get a very small drop in performance. What this means is that neural networks have a lot of parameters which are redundant and could be removed. So this means that we have a lot of extra parameters in my network to begin with. So can we somehow use this over parameterization to try to pack in more and more tasks inside the neural network? So if I just have one model, you can ask the question, how many tasks can I pack into that one model, right? And can we be clever in how we go about doing it? So, one idea, over here is proposed in a work called superposition of many models into one. I'm again not going to go into it, but it's a pointer if you're interested in looking more in how we end up doing this. So next, what I'm going to talk about are different kind of assumptions that are typically made in continual learning. Right? So there is this nice paper called Three Scenarios of Continual Learning, which if you want to give an overview of different problem setups, it's an excellent reference. So the first setup is where at test time, what we assume is that I know the task ID, right? What do I mean by this, right? So consider a setup where an agent has to find a goal. The agent is trained on many different environments, and the goal looks different in different environments. So what this means, the task incremental learning setup means is, given the environment, find the goal. That is, I'm telling you what environment you are in. Right? For example, maybe environment 1, the goal is red. In environment 2, the goal is blue. Environment 3, the goal is green. So I tell you, you are in environment 3. Now find the goal. So to give, another example, suppose we have, task 1, task 2, task 3, and so on. Each task requires us to classify the image as belonging to a first class or a second class, right? But each task has different pairs of images or different pairs of classes, right? So the task incremental learning is saying, given a task, suppose I said it's task 3, does the image belong to the first class or the second class? So that is the most straightforward way of doing sequential learning, where the task ID is known. Now the second, a more complex version is when the task ID is not provided. Right? So this is what is called as domain incremental learning. I think these names are not important, but just knowing this classification is important, so that once you see a new paper, you know where to map it, right? So again, going back to the same example, that we had goals which look different in different environments. Now, the agent needs to find the goal, but it is neither told what the environment it is in. It can infer it on its own, but it is also not required to identify which environment the agent is in. Right? So it just needs to go and find the goal. So for example, with the task, so for example, over here, I can choose, any one of these tasks, and I can say, well, is this a first class or a second class? For example, if you get any of 0, 2, 4, 6, or 8, you should say it's a first class. If you get any of 1, 3, 5, 7, or 9, we should say it's a second class. So over here, I'm not giving the task ID. A third, scenario is where I need to solve the task, but also tell you which environment I am in, right? So it's like find both the goal and also in which environment the agent is in. So, for example, over here, I need to tell you pretty much, what digit do I have? Is it 0, 1, 2, 3, or, up till 9, right? So now this, ends up being the most, general version of the problem. Now, if you look at some of the works that we discussed, for example, look at progressive networks, they required task ID both at training time and at testing time, right? Why did I need it at training time? Because I was constructing one column for each task. Why do I need a testing time? Because I need to know from which column I should read the output. So I require the task ID both at train time and at test time, right? So progressive networks require task ID everywhere. Now, elastic weight consolidation. Now they require task ID at training time, right? But they don't require task ID at test time, because at test time I have a set of parameters which works for a bunch of tasks. But I do require task ID at the training time. So one question you've been asked is, how do we go about inferring task ID? So to motivate, one of the latest paper in this area, I will first just briefly introduce this idea of hypernetworks. So what are hypernetworks? So typically you have a network where we have an input X and it gets processed by some weights W1 to get to features H1, then weights W2 and so on, right? So typically we assume weights are our parameters that we are optimizing. Now, instead of optimizing the weights, what we can do is we can have a second network which predicts the weights of the first network. And these networks are called, and these kind of networks are called as hypernetworks. So I have a second network which predicts the weight of the first network, and then we train both the networks using SDD. Right? That's the high level idea of hypernetworks. So now, there is this a bunch of works or a whole line of work which is looking at how can we learn these task conditioned uh, hyper networks. And what do I mean by this? Now suppose I have my input X and I have my output Y, and we are learning this function which maps X to Y, right? Now if my task is changing, right, suppose my task is X1, task 1, task 2 and task T, then I probably need different set of parameters for each of those tasks. Right? So what I want to learn is, somehow to infer what the task is and then to produce the parameters for that particular task. So, typically the way these works, operate is, they suppose they learn, suppose I have done, 3 tasks until now, and I am getting some new data. What I will say is, well, if I have done 3 tasks, I have task embeddings for 3 of these tasks, say E1, E2, E3. Now I'm going to try to perform this task with any one of these embeddings, and then I can say measure the uncertainty in my performance. And if my uncertainty is very high, then I will infer it's a new task, right? And then try to infer a new task embedding which will produce the right set of weights so I can solve the new task. So, this is the general intuition behind, this line of work. There are other papers such as Film or Mint. I think if you're interested, I encourage you to look at them. I mean, my purpose with, these, maybe these 2 slides is to point you to the relevant literature where you try to infer the task ID and maybe how, given a task ID, we can generate weights of for a new task, right? And Film and Mint are also ways of modifying weights of a network depending on some side information. Then some nomenclature I think is good to get it straight. I think sometimes it can get very confusing. So one term that you will hear a lot is multitask learning. What this means is, we are trying to solve multiple tasks simultaneously. That is, all the tasks are given to me at once. But multitask learning by itself does not concern itself with transfer, right? I can do multitask learning by saying I've learned well on all the tasks, but I may not be required to transfer. Transfer learning is saying I want to reuse knowledge from past tasks to transfer to new ones, right? But I could transfer from just a single task, or I could transfer from multiple tasks, right? Transfer learning says nothing about how many tasks I am training on before I end up transferring. And few shot learning is just a variant of transfer learning. Then, there's other term, which is continual, sequential, lifelong learning. All of these pretty much refer to the setup where the tasks are coming in sequence, and how can we learn these tasks. Now, continuous, sequential, lifelong learning may or may not concern with transfer, right? I mean, ideally, what we would want from continual/lifelong learning is that we want not to forget, but transfer. But, turns out, what has happened in the research community as is continual and lifelong learning. Most of the research in this area has focused on overcoming catastrophic forgetting, but has not really looked at transfer learning. Now, transfer learning has looked at learning from few examples, but they assume that all the tasks are given at once. Right? So, ideally what you want is, to be learning continually, but also being able to transfer. The reason this is hard is because there's a fundamental trade-off between remembering and sharing parameters. Right? For example, if I remember everything about task one, then I will not be able to change the parameters, because if I change the parameters, then I might forget something about task one. But if I don't change the parameters, I may not be able to transfer my knowledge, right? So there is this tension between remembering old things versus sharing knowledge to perform new things, right? And if you want to look at one reference in this, I would point you to this paper, Learning to Learn Without Forgetting. So I think it's a good paper which describes this problem. So with that, I'm going to stop and take any questions.